everybody. Welcome to another edition of HL Chemistry Flipped Classroom. I'm your host, Mr. Los, and it will be my pleasure today to talk to you a little bit about ionic bonding. I'm going to give you an introduction and hopefully help you understand what that's all about. So, when you have ionic bonding, formation of ionic bonds first requires that neutral atoms attain a charge. So in other words, what I'm telling you here is that ionic bond requires ions. Now, before you accuse me of being Captain Obvious, you'd be surprised at how often students make that mistake or sort of forget about that down the line. But, you know, let's use this scientific terminology, let's use the information that's put in front of us, and please never forget that ionic bonding indeed does require ions and that charged particles be present. As we've probably talked about in the past, ions are generally going to have a full valence shell and they're going to be more stable than the parent atoms that form them. So, again, just as a kind of a reminder of how this works, take a sodium atom. Atoms by definition are neutral, 11 protons, 11 electrons. It has this one electron in the outer shell. That's unstable. What it tends to do is lose that electron and form a sodium ion, an Na+. And so now it has the stable formation of 8 electrons in the outer shell. If we look at that one more time, atom to ion, it loses one electron, becomes Na+. How about chlorine? Chlorine atoms have 17 protons and 17 electrons, so there's, if you count them, 1, 2, 3, 4, 5, 6, 7, I think, electrons in that outer shell, or there should be anyway. And what chlorine will tend to do is gain an electron, become a chloride ion, and have a -1 charge. So when we're dealing with ionic bonding, at the very least we have to have ions, and never forget that, please. Remember Captain Obvious. Some terminology. Octet, 8 electrons in the outer shell. That's a term we'll throw around quite a bit in the bonding unit. That's a particularly stable configuration. Again, Captain Obvious might note that oct, as an octopus, is a common thing that you see associated with the letter 8. Electrostatic attraction is a fancy word that means opposites and negative attracting. Opposites attract. So it's also kind of known as Coulombic attraction, but if you've got opposite charges, they're going to be drawn together. So to formally define an ionic bond then, an ionic bond is a bond formed between oppositely charged ions due to electrostatic attraction. Now, usually this is going to be between a metal and a non-metal. Now what this especially highlights is how things in chemistry build upon themselves. For instance, if you have no idea where to find a metal and a non-metal on the periodic table, like we talked about in the last unit, you're going to have some trouble here. There's a periodic table. Look at it. Can you point out where the metals are? Can you point out where the non-metals are? Go ahead and do it. Nobody's afraid. No, don't be afraid. Nobody's watching you. Go ahead and point. Point on the screen. Point to some non-metals. Where are they at? Where are the metals at? Did you point up here for the non-metals? The non-metals are in this corner. Now, of course, the noble gases are non-metals, but they're usually not involved in bonding. And then all our metals are all over here, like all these over on this side. So pretty much the whole left side of the little stair step you may or may not have drawn in on your periodic table. So when we have an ionic bond, we have something from this side bonding with something from this side. It's one way we can tell when we're dealing with an ionic bond. A couple of other terms that we've already defined, but just to remind you, a cation means a positive ion. One way to remember that, if you like cats, and cats are positive to you, perhaps that's how you remember cations are positive. Anion means a negative ion, or I think of anion as a contraction of a negative ion. That's how I remember that anion is negative ion. Now that we got that terminology out of the way, let's look at one of our big ideas here. Now, big idea. Whoa, this is important. This is serious. Sometimes, I don't know, I don't feel serious enough, so I call in with a little help. This is Samuel L. Jackson. He's a serious man, and he's imploring you to think about these things and do your best to wrap your brain around them. This is a big concept, that's going to carry through this entire course. When a bond is formed, no matter what, electrons are shifting to a lower energy, more stable state than they were before. In other words, they're going from a high energy state to a low energy state. So what this means is energy is released in the process. Bond formation is exothermic always. Every type of bond, when we're talking about chemical bonds, every type of bond that is formed, energy is released when that bond forms. And the opposite is true if you break a bond. Breaking bonds is endothermic. It means energy is absorbed. It means that takes energy. So again, huge idea in this course. I even had Samuel L. Jackson come around to help us emphasize the point. Bond formation is exothermic. Energy is released. Bond breaking is endothermic. Energy is absorbed. Now, just to kind of help you see this, let's look at the reaction between Na and Cl. So far we've been talking about Na forming an ion, becoming Na+, Cl forming an ion, becoming Cl-. What happens when these two things actually form and undergo a chemical reaction? What does it look like? Well, let's check it out.
A small piece of sodium metal is placed in a flask containing
Little piece
yellow
of sodium,
chlorine gas.
chlorine in here.
The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass.
So the chlorine's in there, you can't really see it. The reaction hasn't started.
Initially, no
I'm just going to
reaction
put a
is
little water in
observed
here to
between
get the
the
reaction
sodium
started,
and
and
the
we'll see a
chlorine.
bond
The
formation
reaction
event.
will be initiated by adding a drop of water to the sodium.
So that's what I'm talking about when I say bond formation is exothermic. Look at this release of energy as this ionic bond forms between sodium and chlorine to form, good old table salt, NaCl. So think of that video when you think of bond formation and bond formation being exothermic, all that energy being released. So in the formation of an ionic bond, what happens is electrons are transferred between atoms to achieve an octet. So an atom loses possession of an electron, one atom gives an electron, the other takes it. And what happens is they'll form charges, but these charges will always balance out to produce a compound. So sodium +1, chloride -1, +1, -1, those charges balance out for no charge overall. When we're writing ionic substances, writing formulas for them, which we will do soon, its charge must be balanced. It must have a neutral charge overall. Now notice this is in an ionic bond. Captain Obvious says ionic bonds require ions. In other types of bonding, it's totally different. The situation is completely changed. I'm talking about ionic bonding now. The charge will always balance out, and we should always be thinking about that when we're thinking about the formula of ionically bonded compounds. Compounds that do a different kind of bonding, it won't necessarily be the same story. So, just as a for instance of what I'm talking about, again, we will look at sodium and chlorine. Sodium atom, chlorine atom. Sodium has an extra electron. It has this one electron in the outer shell. It would like to lose that electron and go back to have a full shell, like I showed you before. Chlorine atom would like to gain an electron, gain one electron to get 8 electrons in its outer shell here. So, in that video you saw a few minutes ago, obviously we can't see any of this with our naked eye, but what we were seeing was sodium losing an electron, chlorine gaining one. They form ions, sodium ion, chloride ion, and then these two ions stick together. So that overall process releases a tremendous amount of energy, as you saw in that video. And then we will form a crystal of NaCl. So that's what I mean by electrons are transferred. Sodium loses an electron, chlorine gains one. It's a transferring. So what you form when you do an ionic compound is a crystal lattice. A crystal lattice is a network of positive-negative ions in an ionic substance. So it looks a little bit like this. Here's kind of an artist rendering of one. Notice we have the small sodium ions. If you think about when we talked about ionic radius in the last unit, ions of metals are smaller. whereas ions of nonmetals are bigger than their parent atoms. But you form this big matrix, this big crystal lattice, and imagine even one tiny, tiny, tiny grain of table salt. Imagine that. Even in that tiny grain of table salt, there'd be billions and billions and billions of atoms. Basically, that little crystal would be, that entire thing would be made up of a network like this, of Na plus and Cl minus. So there's lots and lots of Nas and there's lots and lots of Cls in each little crystal. So when we write the substance, what we're actually doing is we're writing the lowest ratio. In the crystal, there's always one sodium for one chlorine. That's why it's written like this. Now, in a different type of substance, like for instance, this would be called calcium fluoride, we write that CaF2 because in that structure, there's 2 fluoride ions for every 1 calcium. Or Fe2O3, which is rust. It would have a lattice where there's 2 ions of iron for every 3 oxygen ions, oxide ions. So technically these formulas are called formula units. They're only the lowest ratio of particles in a crystal lattice. You know, another thing we're going to be kind of talking about throughout this unit is the difference in what results in different types of bonding. Water does a different type of bonding. It does covalent bonding. It exists as molecules. So if we could zoom in on a glass of water, we would see little H2O molecules where there literally is, in every molecule, there literally is 2 hydrogen atoms and 1 oxygen within each particle. This is different than an NaCl. If we could zoom in on a crystal of NaCl, we would see a couple billion Na atoms and a couple billion chloride ions. And in this case, this NaCl is just the lowest ratio. So there are no actual particles where there's literally just 1 Na bound up with 1 Cl. Whereas in H2O, the smallest particle actually really does have 2 hydrogens and 1 oxygen. This can be a tough concept to wrap your brain around, and you know we're going to kind of continue to develop these ideas. But that's one of the first things we want to start talking about is kind of differences in structure that result in different kinds of bonding. And hopefully this makes a little bit of sense to you, and we'll continue to talk about it as we talk about bonding and sort of wrapping our brain around the difference between the way NaCl bonds and the way water bonds and the structures that result. Now, you know, somebody posted this picture, my friend Samuel L. Jackson, that we were just looking at, and he claims his dog looks like Samuel L. Jackson. Yeah, I don't know. That's up for you to decide. So a theme for this unit will be what physical properties result from different kinds of bonding. What are some characteristics of things that have ionic bonds versus other kinds of bonds that we're going to talk about? Well, for one thing, you can talk about ionic substances. They will always, with 0 exceptions, be a solid at room temperature. And they're going to have very, very high melting points. For instance, NaCl, sodium chloride, might melt at like 800 degrees Celsius or something like that is its melting point. Very, very, very hot. Your pan at home probably would not even melt it. I'm certain that it wouldn't. Whereas sugar, actually, which is not ionically bonded, has a much lower melting point, and if you put some sugar in a pan at home and turn on the burner, you'll melt it relatively easily. So ionic substances are always solids with very high melting points. Many ionic compounds, but not all of them, are soluble, meaning they can dissolve in water. What's important, and this is a super critical concept that we're going to look at throughout the year, you know, we're trying to get some of our fundamentals down here. When ionic substances dissolve, what they do is they break apart into their component ions. And I'm going to show you some things to hopefully help you figure that out in just a minute. Aqueous, the term aqueous, abbreviated AQ, it means dissolved in water. So, like, for instance, we could show these 2 ionic substances dissolving. What happens is, when it dissolves in water, this whole thing breaks apart into Na plus ions and Cl minus ions, separated. calcium chloride. When calcium chloride dissolves, the entire thing breaks apart into one calcium and two separate chloride ions, so three pieces. And again, we're going to look at some pictures here and stuff to try to help us figure out exactly what's going on with this. Like for instance in the case of NaCl. So here we have some NaCl. Here's a crystal lattice that we talked about. When you put it in water, here's the water molecules. What happens is the water starts to rip apart this crystal lattice and everything separates. That's what we're trying to show here, is that these Na pluses and Cl minuses actually end up getting separated out. So there's a couple of our sodium atoms, there's a couple of our chloride ions. Here's another thing we can look at. This is a simulation from PhET, P-H-E-T. You can see it up there. Excellent website to go and look at to help you understand all sorts of things in chemistry and physics and math. But this salt shaker contains NaCl, so it's got sodium and chlorine. And when we shake it, when we first shake it, notice the crystal lattice. But as it enters the water, that crystal lattice is no more. It breaks apart into the component sodium and chloride ions. So all those little guys are floating around instead of having the crystal lattice anymore. Something to notice is the number of sodium ions is always equal to the number of chloride ions because of the ratio. There's always a 1-to-1 ratio between these things in NaCl. Now if we look at a different one, like calcium chloride, like we were looking at before, so calcium has a plus 2 charge, chlorine has a -1 charge, so calcium chloride would look a little more like this. Shake that guy in there, still it breaks apart. Everything breaks apart. Except the difference is, now since calcium chloride is CaCl2, there's always twice as many chloride ions as calcium ions when we do that. But still, the same thing is true, that they all break apart. So again, showing you this slide one more time, that's what this is trying to show you. This is the crystal lattice. This is unbroken apart. When it goes into water, those ions break apart and become separate from each other. That was the first little illustration we looked at. The second one, CaCl2, that entire thing breaks apart. The result is each one of these would break into 3 separate pieces. And what's also true is when all is said and done, for every 1 calcium, there's 2 chloride ions. Whereas in the case of NaCl, it's 1 sodium ion for every 1 chloride ion. Now, if that doesn't make sense to you, what I'd suggest is, maybe back the video up a bit, look at the animation again, or maybe even better, go to the PhET website itself. You should be able to find your way there. It's under the simulations. If you go to Play with Simulations, Chemistry, Solubility, I think is the name of it. But I bet you could find it if you dug around there. But through one of those methods, hopefully you can wrap your brain on what's going on with this here. Okay, so a couple more physical properties of ionic substances. They are electrolytes, meaning they conduct electricity when they're aqueous, dissolved in water, or you melt them. Notice they are not conductive when they are solids. They do not conduct electricity when solid. The thing about electrical conductivity, if you know anything about electricity, it's the movement of electrons. Well, that's true, but there are other ways electricity can be conducted. One thing you definitely need, though, is you need charged particles that have the ability to move. That's the only way you can have electrical conductivity. Maybe it's electrons moving through a wire, so electrons are charged and they're free to move through the wire. Or, in the case of ionic substances, it's those ions themselves. Remember, think back to that animation I showed, all those little ions moving around in the water. Those are actually the things that carry the charge in this case. Now, we may or may not have seen a demonstration of this live and in person. I will show it to you if I haven't already. So be sure to mention that to me in case I forget. As I mentioned, ionic solids do not conduct electricity because in that crystal lattice, there's no freedom of movement there. There is charged particles, okay, but they are not free to move in the crystal lattice. So ionic solids do not conduct electricity, but liquids, if you melt them, and aqueous ones do. Just another little illustration here, another little picture. Really, let's not worry about these right now. Let's worry about this guy. When you have an ionic substance, like we took some salt, we dissolve in this water here, electricity will be conducted if there's a battery over here, so the charge will be able to cross this this barrier, if you will, in the water. So in salt water, electricity will be conducted, make a light bulb go on. Whereas something like, let's say, sugar or other things that are not ionically bonded and you dissolve in water, there would be no electrical conductivity. And some can do it kind of in a medium way. And like I said, hopefully we'll look at this demonstration in person if you haven't seen it already. But that's about it. Thank you very much, guys, for tuning in, and we'll see you next time.